everyone, it is the Great American Eclipse Day. I am Caitlin Sachs, a senior producer for NOVA, and we are here in Russellville, Arkansas. The sun is shining and we are in the path of totality. It is coming in just a couple of hours, and we have an amazing hour for you right now. We are going to talk to some NASA experts. We're going to totally nerd out on solar science. We're going to get a behind the scenes look at this amazing NASA live stream setup here. We're going to learn about how that all works. And we're going to talk about how you can enjoy the eclipse safely wherever you are in the country, whether you are in the path of totality or not, it's raining or not. We're going to talk about what you can expect, how you can enjoy it. We are so excited. There's going to be a ton of fun facts. I'm going to start with my favorite because I can't wait. This is the coolest thing that I've learned in all of our eclipse coverage. So the fact that we're having a solar eclipse today here on Earth is a complete cosmic coincidence. It just so happens that our moon is about 400 times smaller than the sun and 400 times closer. So it perfectly blocks out the sun, and it's not always going to be that way. In a few 100 million years, the moon is going to be a little bit further away from the Earth, and Earth will no longer experience total solar eclipses. It is an amazing time to be human on this planet. All right, so we have a fantastic hour planned for you, and the best part is you are going to get to ask your questions to the NASA scientists that we're talking. So put your questions in the comments, in the chat, in whatever it's called on the platform you are listening on, and we have a whole team of NOVA. We have a whole big NOVA team here. Say hi, guys. We have Tara, our producer here. We have Julia, our co-executive producer, the boss of NOVA, going to help get questions to me as well as a team at home at NOVA headquarters in Boston. So put your questions in the chat and we will get them to the scientists and try to answer as many as we can. All right, so let's get started. First, I'm going to invite Bob Loper. He's an astrophysicist at NASA Marshall Space Flight Center. Thank you so much for making some time for us today.
Thank you for having me.
So first, how exciting is this to be here?
Oh, it's amazing. We're really looking forward to this eclipse. It's going to be a beautiful day. We'll get to see the solar corona. Everybody will get to see it here.
Is this your first eclipse? Have you seen it before?
This is my first total eclipse. I've
Mine
had
too.
4 partials before.
Amazing. Okay, so we're going to get into what we can expect from this total eclipse.
Right.
But first, what is NASA doing here?
So we are reaching out to, so Russellville is in one of our service locations. We are coming out with a whole bunch of outreach, encouraging people to get involved in eclipse watching, into looking at solar physics. We're just really hoping to draw everybody into science. And
I understand this setup is also to help the folks who are not in Russellville see the eclipse. So you're going to be broadcasting.
That's right. So this, what you're seeing behind you is a set of solar telescopes that are going to be used in the live NASA TV stream.
Great. So after this live stream is over, you can go over to the NASA's live stream at that's at plus.nasa.gov. A direct link is going to be in the chat or the comments, and actually watch the eclipse live across the country. This is one of, is it 8 locations?
8 sunspots.
8 sunspots where they are going to be filming the eclipse and broadcasting it across the nation. So if you can't see it yourself in totality, that is one way that you can still see it. So in a little bit, we're going to go do a little bit of a tour of those telescopes. But first, I want to nerd out about the solar eclipse and about the
awesome.
So you study heliophysics. Why? So heliophysics, that's the science of the sun, yeah?
Yes.
Why are folks who are studying the sun interested in eclipses? It's not just the spectacle.
It's not just the spectacle, although the spectacle helps draw people in. And I think if we can draw at least even one person doing professional science, that's a win. As far as doing heliophysics, I look at the solar eclipse as an opportunity to look at the inner solar corona. That's the piece as close as we can get to the solar photosphere, the surface of the sun, because the moon blocks out the sun surface so perfectly. Normally we have to, we depend on occulting disks on our spacecraft, which blocks out a little more of the sun than we would like, just in order to keep it stable enough to see.
So I want to back up and break that down a little bit. We're talking about the sun's corona. Before we even get to that, what is the sun? What is it made of, and what is the corona exactly?
Okay, so in the simplest terms, the sun is a big ball of hydrogen and helium, and it is really hot, and so you have this nuclear fusion inside, and energy eventually makes it out to the to the outer reaches of the sun. The photosphere is that visible solar surface, what we like to call the big yellow ball in the sky. That's what we normally see when we look at the sun. But beyond the photosphere, there are other layers of the solar atmosphere. It goes out into the chromosphere and the corona. And the corona is that outer part of the solar atmosphere that really manifests that roiling dynamic magnetism of the sun.
Okay, so so there's this outer layer of the sun, the corona, that we don't usually see.
Right, it's usually too dim to see if you're looking at the sun.
And that's when you've seen, I'm sure many of you have seen pictures of what an eclipse looked like by now, this sort of wispy thing. What creates that sort of wispy look to it? The sun, the rays, the sunshine.
Well, in the solar corona, the gas is so tenuous. There's just so little of it there that it can't help but follow the magnetic field. Okay. So it is magnetically bound. And so what's causing that strange structure is it's following the magnetic field lines away from the sun.
So the sun has a magnetic field, just like
it does.
Tell me about that.
It is so the sun is essentially a big ball of plasma, and because it doesn't rotate like a solid, because the outer regions of it are gas, and so it experiences what's called differential rotation.
Okay, so a plasma is like, you have like solid, which is hard, liquid that's sort of fluid, gas, and then plasma is something else that's like a fourth state of matter that...
Yeah, when people call it a fourth state of matter, it is essentially ionized gas.
Okay, so it's the atoms that have lost some of their electrons, so
that's
it's like
right.
Beyond gas, and that's roiling and boiling, and
that's right.
Boiling is probably not the scientific term. Sorry, fact checkers. But okay, so it's moving around.
That's right. It's moving dynamically with the magnetic field,
and so creates this magnetic field.
Right. So as that ball of plasma, that ionized gas rotates, the equatorial region of the sun rotates a little faster than the polar regions, and so it drags. There's a magnetic field that's formed, and it drags around the sun.
And sort of bends those, and that's what we're seeing when we see those wispy corona.
That's right.
It's the plasma. Is it plasma along those magnetic fields?
It's plasma along the magnetic field lines.
Very cool. Hot tip, if you want to see visuals of this, you can watch Nova's Great American Eclipse on our website after you enjoy the eclipse today, because you shouldn't miss it for that. So corona, there's some mysteries about the corona you're trying to figure out. Tell me about those.
Well, the biggest mystery is how the corona is so hot. We don't really know. I think that's one of the biggest questions in solar physics, is the region below the corona is only tens of thousands of degrees Kelvin. The solar corona can reach as high as millions of degrees Kelvin, and we're not quite sure how that happens, how that outer atmosphere gets so hot. There's some energy mechanism that isn't quite understood yet. We're still researching.
Interesting. So just to restate that, to make sure I understand it clearly, the surface of the sun is hot, and you'd expect it to cool off as you move outward, but it doesn't. It gets hotter as you move out. And you're trying to understand that from looking at these eclipses.
Right.
And so are you going to figure it out today?
Oh, if I could figure it out today, I'd be the hero.
Tell us a little bit about what some folks have been talking about, that we're at a solar maximum. What does that mean?
So the sun goes through periods of magnetic activity. So I mentioned those magnetic fields inside the sun get sort of pulled about by the differential rotation.
Because of the churning.
Because of the churning. And eventually you get some darker regions on the sun that are called sunspots. And we gauge solar magnetic activity by how many sunspots we see. So the solar minimum, there's a relatively little magnetic activity, fewer sunspots. Solar maximum, which is what we're closer to now, we see more sunspots, more magnetic activity, and we'd expect to see a more active solar corona when we look today.
So we're going to get a better show than we got last time.
We would like to see, we'd like to expect a better show today than we saw in 2017.
Okay, because the cycle is, you said it's a, how many years?
It's an 11-year cycle.
And so back then it was minimum, now we're at maximum, and so the corona will be more interesting, basically.
It should be more interesting.
It'd be prettier. All right, another reason to get out there. I understand that another big difference for scientists between this eclipse and the last one is that since 2017, we've actually sent a space probe to touch the sun.
That's right. We have Parker Solar Probe. In fact, the Parker Solar Probe's closest approach to the sun bookends our heliophysics big year. So we started our heliophysics big year in October of last year with the annular solar eclipse. This total solar eclipse is part of it. And then finally, Parker's closest approach to the sun on Christmas Eve of 2024 gives us the end of our heliophysics big year. It's a 14-month period, but you round it to a year because it sounds better than saying heliophysics 14 months.
Yeah, it's all just, planetary rotation.
Yeah,
years are flexible.
But we launched Parker Solar Probe 2018, I think it was, and it's been steadily getting closer to the sun as it gives up energy to Venus. And we've done, I think, our last planned orbital flyby of Venus.
So I understand it's actually touched the sun. How is that even possible? I mean, it doesn't burn up. What?
So it is very well constructed with a very robust heat shield, so that it can survive being in the solar corona. And that's what we mean by touching the sun. It has already touched the sun. It's touched the solar corona and measured a lot of good stuff within that I think will, in the next 5 to 10 years, it's going to change physics textbooks.
Wow. Today, is it going to be collecting data that in some way is important to the solar eclipse? I mean, how does what it's doing today?
So it is measuring the solar corona, and we are measuring the solar corona here on Earth. So different observers, different locations,
different data points,
different
perspectives. Cool. So when did Parker get to the sun essentially?
Oh, let's see. It got to the sun, I want to say a few months after it launched, 2018. So it actually did a few orbits where it gave up energy to Venus so it could decrease its orbital distance. And I think now it's about a quarter of an astronomical unit from the sun at its closest approach.
So it's been there several years. Have we learned anything from being able to touch the sun?
Absolutely. The thing that comes to mind is these magnetic switchbacks that we've seen. We've seen the magnetic field as you go further and further from the sun out in the solar past the solar corona into the solar wind. You've seen this strange magnetic structure called a switchback, where the magnetic field line will suddenly switch back and then go back out. And you see that through the plasma interactions.
And so what does that mean to have magnetic fields going in and out like that?
I'm not sure yet.
Does it basically mean the atmosphere of the sun isn't smooth? It's like bumpy?
Yeah, so it's bumpy. It means there's some interesting phenomenon going on where the solar corona ends and where the solar wind begins. There's some rapid change that occurs.
Are you getting any closer to figuring out why? Is this helping you get any closer to figure out why that corona is so hot?
I think so. Yeah, so I think any data that we can look at in the outer solar corona can help. I think that's another data point. We're looking at any sort of phenomena that can help explain why the solar corona is heated.
Great. So some folks have been asking us about the International Space Station. Mm-hmm. Are scientists on the space station able to view this eclipse and also add data to NASA's sort of research?
Yes. So the astronauts on the space station have a unique view in this eclipse. My understanding is they'll have 3 passes where they'll have access to the eclipse, and they'll not only be able to see the eclipse from below, looking up at the moon and the sun, but also looking down and seeing the moon's shadow sweep across the Earth.
Yeah, and so an important thing to understand is what being in a total solar eclipse means. Is it means the moon's shadow is landing on the Earth wherever it's passing over. So my last question to you is, what are you most excited about today?
Oh, I'm most excited about seeing my first total solar eclipse.
Me too. Great. Thank you so much. We are going to transition actually to answering some questions. We have some questions teed up from some classrooms across the country. Our first classroom is going to be Megan Parker's classroom from Russellville, Virginia. I'm going to wait a moment to make sure we can get Megan on the stream. And I'm gonna get her question and convey it to you.
Okay, hello. We're really excited here in Northern Virginia and Hillsborough Charter Academy. We have our third graders here, and we have some kids that have some questions for you. So I'm going to turn it over to our scholars.
All right, third graders.
Right here, buddy.
So my name is Miles Clarkson, and my question is, why do we have to wear eclipse glasses to look at an eclipse and not just regular sunglasses?
That is a great question, Miles. I'm going to ask it to our scientist. Why do we have to wear eclipse glasses today instead of just regular sun?
Oh, that's an excellent question. Remember, your parents, your mom, your grandma always told you don't look directly at the sun. It is dangerous. The sun is really, really bright, and the eyes are really, really delicate. And you certainly don't want to stare at the sun for the long period of the partial eclipse we're going to have. So we here in Russellville will see about an hour and a half of partial eclipse before the total eclipse and about an hour and a half after. And you don't want to stare at the sun for any lengthy period of time without solar eclipse glasses. That blocks out a large part of the sun's energy.
Great, thank you. I think we have time for a few more questions from Miss Megan's classroom.
Yes, our next scholar with the question, introduce yourself and ask your question.
My name is Amelia Lapina. My question is it more dangerous to look at the eclipse than the sun by itself?
Is it more dangerous to look at the eclipse than the sun by itself?
So if you're in the total eclipse, if you're during totality, you can look at the sun to your heart's content. I think the danger is at the very beginning, at the very end, where you still have a partial eclipse. See, our human instincts are to not look at the sun directly because it hurts. But if we're looking for a total eclipse, we might be tempted to say, I'll play through the pain a little bit and stare at the sun for a while. Don't do that.
Not a good idea.
Don't do that.
So it's just as dangerous to look at the sun as it is to look at a partial eclipse.
Yes.
But it's safe to take off your glasses once you're certain.
Once you're in totality.
That the total solar eclipse has started. That's a really great question. We have time for one more question.
Perfect. We have one last scholar with an awesome question to make us do some critical thinking. Go ahead and introduce yourself.
My name is Leo Phillips, and my question is, what would it look like if I was standing on the moon during the solar eclipse?
I'm sorry, you said it was, Leo was your name?
Leo Phillips.
Can you repeat the question one more time?
Yeah. What would it look like if I was standing on the moon when the solar eclipse happened?
Oh, that's a great question. What would it look like if you're standing on the moon during a total solar eclipse?
Oh, wow, that's a great question. So if you're standing on the moon, so I should say if you're on the Earth-facing side of the moon and you're facing the Earth, it's going to get dark for you because you are still in the shadow of the moon. But you'll get that nice view that the space station astronauts also get, is you'll not only see it dark for you, but you'll see that shadow of the moon going across the Earth.
Cool. And what if you're on the other side of the moon?
If you're on the other side of the moon, you're going to see full sun. It's going to be full daylight. Wear your sunblock.
That's great. Thank you, Megan Tucker's classroom from Purcellville, Virginia. We have one more. We actually have the Choctaw Cultural Center in, is it Caldera, Oklahoma? Did I get that correct? So we have Matthew Ellis from the Choctaw Cultural Center.
Halito, my name is Matthew Ellis. I'm a member of the Choctaw Nation. I study mechanical and aerospace engineering at Oklahoma State University. So my first question, I'm really interested in the research part of everything to do with the eclipse. And there's the nationwide eclipse ballooning project that is critical to NASA's mission with eclipse research regarding the Earth's weather and atmosphere. So I wanted to ask, why is this collaboration with outside institutions so important to NASA's mission of research during this eclipse?
That's a great question. So NASA has a collaboration with, you said it was the ballooning project?
The nationwide eclipse ballooning project.
The nationwide ballooning eclipse project. as well as I think some other collaborations nationwide. Why is it so important to, I mean, you're NASA, why do you need all of these collaborations? And maybe tell us about a few of them, what they are.
Yeah, so in fact, NASA is not just for space, though space is the largest, is the most visible part of what we do, but we also study the Earth, we also study the air, and in particular what we're doing is, during the eclipse, we're looking in part at this ballooning collaboration to help us study what the atmosphere does in response to the eclipse.
Very cool. Are there any other other sort of citizen science projects that NASA is working on, like is collaborating on?
Yes. So I believe there's an app called Sun Sketcher, I think it's called. You might check me on that, but it's an app that people can have, people can download, and they can use that during the eclipse to sketch the shape of the sun to help us study more about the sun.
That's great. Matthew, I have a couple questions for you. First of all, you're from the Choctaw Cultural Center. Where exactly is that? Because I can't read my notes, and I want to make sure I didn't get it wrong.
Calera, Oklahoma.
Calera, Oklahoma. And I'm wondering, sorry to put you on the spot, but can you tell us a little bit about your community's traditions around eclipses?
So yeah, we have a presentation going on. It just happened before this live stream about the Choctaw. In a long time ago, the Choctaw tribe was the sun was very important to them, and they very naturally got afraid when the sun went away. They didn't understand the science behind it. Not many people did. So they made up a story that a squirrel was eating the sun. And just similarly, how you would scare a squirrel out of a tree if it was, on Earth, they would throw pots or, shoot their arrows at it to scare the squirrel away. So that's what they did when there was a solar eclipse. I think there was, it's confirmed that they experienced one full solar eclipse during the tribal times.
Oh, and when about was that?
I do not know the specifics on when it was, but
no worries. Well, thank you so much for sharing that. I think we have time for one more question from you, Matthew, if you have one.
Yeah. Again, like with the massive amounts of research that NASA does, like across the nation, across the globe, that's not only happening today with regards to the corona and the sun, but all the time, like you said, with the Parker Solar Probe. How does NASA go about like processing all this data and all their findings? And when can the public expect to see these discoveries published and made public?
That's a great question. So with all of these data collection programs that NASA is part of around the globe, we've talked about Parker Solar, these collaborations with, for example, the ballooning project. How does NASA process all of this data, and when can the public expect to sort of see the results of the data coming from this eclipse?
So we now have an open science data initiative where we're encouraging investigators to release their data within 6 months of collecting it, which then makes it available to anybody to look at and to investigate and to try to answer their questions. For instance, I find most of the data that I use personally on the Space Physics Data Facility, SPDF. So if you do a Google search for NASA SPDF, you'll find it. Yeah.
That's great. I think we have a few minutes to take some questions from our virtual audience before we get our behind the scenes tour of the telescope setup. So if the NOVA team at home wants to pass me a question, if we have any. Oh, that's a great question. Okay, so once we see the solar eclipse, and so we're in the shadow of the moon, how much will the temperature drop across the planet, or at least in the past?
You can generally expect the temperature to drop by around 10 degrees.
Okay, about a 10 degree in that Fahrenheit or Celsius?
Fahrenheit, yeah.
Fahrenheit, 10 degrees
that's
Fahrenheit.
a good question too.
I think most of the folks in the US are thinking Fahrenheit. So 10 degrees Fahrenheit is a great question. What else? Okay. So why and how does the weather change when there is an eclipse, and why is that?
So that's part of what we're studying. We do expect that there's going to be a cooling. So we see that because, I mean, it's just like if you go under a shade, it gets cooler, except during totality, the entire city is going to be under shade. We also look at the...
I'm looking forward to that right now. Let's get this eclipse started.
We also look at the ionosphere. We look at the upper atmosphere has a structure that is partly ionized, and we do experiments on that to see how the plasma response occurs there. So we have a citizen science program called HAMSci. It's made of a group of ham radio operators who do transmission during an eclipse to try to access frequencies that are not normally visible in the daytime.
So the frequencies of radio transmissions are different during day and night?
Right. So the frequencies of accessible shortwave radio are different in day and night because the sunlight will excite the atmosphere and ionize the atmosphere partially, and prevent some transmitted frequencies from going through.
Very interesting. Are there any other questions? Ooh, how do they figure out the exact time, and I'll add place, of where an eclipse is going to happen?
That's a great,
so random.
that is a great question, and it is pretty well known how to predict eclipses with pretty good precision. People have been doing it for thousands of years. It is you understand the orbit of the moon around the Earth. You understand the orbit of the Earth around the sun, and then you begin to calculate what's called a three-body problem. So we have the Earth. It is a good show, but it's also a classic physics problem. So the classic physics problem is two gravitating bodies. You can pretty much plot analytically their motion. You put a third body in there, and the classic three-body problem can't be solved just on traditional pencil and paper, but has to be calculated numerically. And so you do this sort of iterative calculation where you're calculating a next step in time, and you calculate the next step, and so on and so forth. And you can use that to calculate the locations of the Earth, the Moon, and the Sun relative to each other with pretty good precision. And you can use that to calculate with pretty good precision when and where you expect to see eclipses.
Great. And to be clear, even though it is a three-body problem to predict the eclipse, this has nothing to do with aliens in the real world. Also, I'll add, NOVA's Great American Eclipse does go into detail about some of the history of predicting eclipse, going back to the ancient Babylonians, some of the indigenous peoples' traditions, and up to sort of modern predictions. So if you want to go on a deeper dive for that, you can check that film out on our website. Thank you so much for your time. I think we're going to pivot now to checking out the telescopes, but super appreciate you joining us today.
Thank you for having me.
A blast today.
I'm looking forward to it.
Thank you. I'll steal your microphone and pass it on to Joe. So Joni, if you want to come over here. And Joe, why don't you come on over on this side? I'm going to give you a microphone so everyone can hear you.
Livestream is still ongoing, but Matthew.
Hi.
Hi.
So everyone, this is Joe Mattis, the manager in the Human Landing System program at the Marshall Space Flight Center, and also, importantly for today, one of NASA's solar photography experts.
Yes.
Thank you so much for joining us.
Well, thanks for having me.
We want to get the behind-the-scenes tour of how NASA is going to be broadcasting this eclipse
Sure.
to everybody.
Okay.
So, what do we have here?
We've got two setups here. We've got two telescopes mounted to tracking mounts, as they're known. They allow us to follow the path of the sun across the sky. The Earth rotates, so the sun appears to move in the sky, and these are set up to make the sun appear motionless in the field of view, so that we can see what's going on over the course of time. On this particular setup, we have a solar telescope called the Hydrogen Alpha Solar Telescope. When you take white light, and pass it through a prism, for example, it breaks into the colors of the rainbow that I think we're all familiar with. Red being one of the colors out of that rainbow. And if you look at a very tiny slice of the red part of the spectrum, the red part of the rainbow, there's a lot of interesting features that could be seen I'll call it the surface. It's really the outer atmosphere of the sun, the chromosphere. Lots of things to see. So this telescope allows us to see that.
And so this telescope is to look at the sun, not during an eclipse.
This telescope can look at the sun anytime, but during an eclipse, the moon blocks all of the light from the sun except for a very tiny fraction, and we can't see anything. So yes, that's
okay. So this is what
correct.
we normally use. Not as good as studying the sun as during an eclipse.
That's correct.
But to see the eclipse, we hop over to the next telescope.
Yes.
Okay. So let's come over here. So
yeah,
for the partial eclipse or the total eclipse or both?
This scope is set up to view the entire eclipse from now through totality and on the other side. This is what we call a white light telescope, which just takes that whole visible spectrum of light and allows us to see it. I have a special filter on the front made from a material called solar film, which is specially designed to reduce the amount of energy that passes through the system to the camera lens in this case, or if you're using it on solar glasses, that would reduce the solar energy to your eyes, making it safe to view.
And so I want to talk a little bit more about the importance of having a filter on your telescope. So if you are viewing the eclipse with a telescope, I understand that solar eclipse glasses do not cut it. Is that right?
Right. Yes, you need to have a filter in place over the, as we call it, the objective lens in front of the optical system to cut the energy down to reduce the amount that reaches your eye. Because your eye is essentially a giant, well, it's a magnifying glass. So it concentrates all the energy down to a little fine point. If you can reduce the amount of energy that goes in, there's not much coming out the other end. But if you try to put it at the other end, which would be the back surface of your eye, it'll burn you and permanently blind you.
That does not sound fun. Can we just kind of see what happens if we put some solar eclipse glasses in front of a telescope?
Sure.
All right. Do you need a card or something to set up?
Yeah. This is obviously a very large camera lens.
This is a big camera lens, but it's essentially a telescope.
It's essentially a telescope, also a magnifying glass of sorts, and also represents your eye because your eye has an objective, has a lens in the front, and it concentrates the energy down to a small point. So now if I can get this adjusted so we can, if you would lower your card just a little bit, see if we can get the sun to come through here. There we go. Right. And I think people that have played with magnifying glass are probably familiar with this. So in your eyeball and in a camera system, the light gets concentrated until it's in focus.
Ooh, it's very bright.
And it keeps getting very bright. I can't even look at it without glasses.
Okay, so if I put glasses in front of it.
If you put glasses in front of it,
what would happen?
This would represent looking through an unprotected telescope. And this is what would happen to your eyeball.
Oh my gosh, I can't even look at it.
And we can see it would be permanent and irreparable damage to your eye.
Oh my gosh. Okay, so don't look through a telescope with eclipse glasses. You need a special.
You need a filter on the front of the telescope or in front of any optical system to make for safe viewing. Absolutely.
Thank you. Okay, so NASA has their telescopes set up with the appropriate filters, and they will be, that's all connected up to this computer, and they will be broadcasting that on their live stream that starts at 1 p.m. Eastern.
Yeah.
Noon Central. So if you want to actually watch the eclipse and you're not in a place where you can get outside and do it, or if you are, you kind of like want to watch it on your phone, which is what I'll be doing, then you can go to plus.nasa.gov. There's a more direct link in the comments or description of this stream. Last thing I want to talk to you about, the eclipse is starting like in an hour for many people. If you don't have glasses, you don't have a telescope, are you just out of luck? No,
there's other ways to view the eclipse. You can view it indirectly, not by looking at the sun, because that would be very dangerous, as we talked about. But I just happen to have a fancy thing called a pinhole viewer. This just happens to be a map of the United States, but it's basically a card with a hole punched in it. You can take a hole punch, punch a hole in there, a pencil or what have you, and you can hold that. If I can take your card here, you can hold that to where you can see the sun through the hole and get yourself adjusted and project basically the sun onto a card. And then as the moon starts eclipsing the sun, you'll see various phases of the eclipse. And depending on where you are, you'll see more or less. And if you're here, you get the total eclipse, so it'll totally disappear. And only during a total solar eclipse can you safely view the sun directly. But otherwise you need to use a device like this or specialized filters to view the sun.
And this is just another form of projection. the
Correct.
sun, just like telescopes.
Yep.
So this is a way that you can still enjoy the telescope. Sorry, you can't enjoy the telescope if you don't have one. Another way to enjoy the eclipse or a
Mhm.
partial eclipse
Yes.
if you don't have glasses. Great. Well, thank you so much.
All right.
Best of luck. We're all going to be watching, so we'll try to tread carefully and not move.
Thank
your
you. I appreciate that.
telescopes.
You can have that.
Oh, thank you. And you can do these pinholes just by poking a hole in like a card or anything like that. Great. So, yep, thank you. Next up, we want to talk to you about how you can get out there and enjoy the eclipse yourself, wherever you are in the country, whether or not that's the path of totality or not. For that, I have scientist Patrick Kane here with me. Patrick, you mind kind of stepping right in here? And I'm going to have you put this in your shirt, go off with it, just like that. Okay. So
Right here.
Patrick is a heliophysicist at NASA, knows all about eclipses, and he is going to walk us through the next few hours of today. So, Patrick, it is 11:30 Central, 11:38 Central, 12:38 Eastern. What is going to happen first today? What's the first part of this eclipse that's going to happen?
All right, the very first part of it is what we're seeing right now. Okay, absolutely nothing except the disk of the sun. But as we get closer and closer to the beginning of the eclipse, which isn't that far away, we'll actually see a little bit of a bite being taken out of the sun. If we were to pull out our official eclipse glasses and put those on, safety first, we would see just a little bit of a nibble taken out of the side of the sun. And over the next hour and a half or so, more and more and more of the sun will disappear behind the disk of the moon.
Okay, so let's talk about that how to view that little nibble. We talked about, eclipse glasses, the projection camera. If you are wearing eclipse glasses, how can you make sure that your eclipse glasses are good, not knockoffs, like they're totally safe?
Well, what you don't want to do is test them out on the sun.
Okay.
You want to make sure that you go up to a pretty much any light bulb. It doesn't matter if it's incandescent or LED, just as long as it's bright. And hold the glasses up to the bulb, and you should only see whatever's generating the light. You should only see the little wiggle of the filament or the LED chips emitting light. You should not see any ambient light at all. Now, you also want to make sure that when you kind of hold them up to your face, you don't see any scratches or pits or anything like that. If you're trying to use old glasses, for example, I've been sticking mine in my pocket for a week now, and they're garbage. I would not use them to actually view the sun. But I will be inspecting any glasses I decide to put on my face before the eclipse starts to make sure that there aren't scratches, pits, holes, anything like that. If there's anything wrong with them, throw them away and get a new pair.
And there's a certain sort of like rating too for glasses.
There's a number that's actually printed on the sides of most of them. It's an ISO number. Is it ISO 12312-2?
Just surprisingly easy to remember.
It really is, and I'm grateful for that.
Okay, so you want to get your solar eclipse glasses, make sure they say ISO 12312-2, and make sure they're from a reputable vendor. There's I think the American Astronomical Association publishes a list of reputable vendors.
Good.
If you have any doubt, if they look like they're worn, use the pinhole method. It's just as good.
Yeah.
Okay, so first we see a bite taken out of the sun if we are anywhere in the US.
Pretty much anywhere in the U.S., yeah, anywhere in the contiguous 48. If you're in Hawaii, you won't see anything. I believe one little part of Alaska will, but if you're in the lower 48, anywhere, you'll see at least a nibble taken out of the sun.
So everyone in the U.S. can see everyone in the lower 48 in the U.S. can see some part of this eclipse. If you're not in the lower 48, you can watch the NASA stream.
That's right.
Okay, what happens next?
All right, so as we get closer and closer to totality, things are going to start to change pretty quickly. The last 10, 15 minutes or so before totality happen pretty quickly. We will start to see the lighting change. We will notice that things are getting a little bit dimmer. If you happen to be wearing a red shirt or a green shirt, you might notice that the color doesn't quite look the same. As you look around, you'll notice that the scenery, that everything starts to look like a black and white photograph that's been hand tinted. You may have seen those. So it's essentially the cones in the eyes aren't as active. So you end up, things sort of take on, it's not exactly black and white, but it's approaching a black and white sort of view.
Interesting. Why green and red and not blue and yellow?
Well, blue and yellow would work as well. It's just green and red are the most obvious.
Okay. Okay, so things start to get weird. And is that
Right.
even if you're in a partial eclipse?
Even not so much. It really, you do really have to be pretty close to totality to notice that particular effect.
Okay.
Now you'll also, if you're really lucky, you might notice some wavy lines on the sidewalk in front of you.
Okay, this is as we're approaching totality.
This is as we're getting really close to totality. That's
Tell me
right.
about these wavy lines.
These wavy lines are, what do we call them? Solar snakes. Some people will call them solar snakes, solar lines, or eclipse lines. They are due to pockets of warm air and cold air in the atmosphere that are distorting the light, the image of the eclipse as it passes through. You know, when we look up at the nighttime sky, we see twinkling stars. Those are due to the path of a light ray sort of getting a little jiggled as it passes through a warm pocket or a cold pocket. Exactly the same effect, but just on a much larger scale. But it is fairly rare to see them. So if you don't see them, you're in good company.
Okay. Okay, so we're approaching totality. What happens next?
All right, just before totality, and I mean just before, you might see
Seconds, minutes?
Seconds.
Seconds before
seconds
totality.
before totality. You might see a bit of a flash of light just on the edge of the eclipse. We call those Bailey's beads. If you have a whole line of them, those are Bailey's beads. If you only see one, we call it a diamond ring. It's really all the same effect. But if you know, when we think of the moon, we think of it as a perfectly smooth sphere. It's not. It has mountains, it has craters, it has gaps in between mountains and craters. So you can imagine watching a sunrise or a sunset through a couple of mountains. Well, these Bailey's beads are due to sunlight passing through that little valley between those two mountains and making it all the way down. It's a beautiful effect. It's fairly rare. You may or may not see it. You have a better chance of seeing it than you would seeing the snakes.
Okay.
And we're really hopeful we'll see one here today.
And so, okay, so we're approaching totality. How do you know when totality has started and you can safely take off your glasses?
Okay. So all along, from the first nibble all the way up through Bailey's beads, you have those glasses on. Once totality starts, you won't actually see anything through your glasses. If you're looking at the sun through your glasses and all of a sudden you can't see anything, totality has started. So it's time to take those off.
Great. Okay. We're in totality.
We are in totality.
Tell me the experience.
Well, this is actually my first eclipse, so I will
right.
tell you what I think is going to happen.
Okay.
What we'll see during totality is the outermost layer of the sun's atmosphere. We call that the solar corona.
Yeah.
That is a really interesting region of the sun at the photosphere, the lowermost parts of the atmosphere. Temperatures are 6,000 degrees. And out in the corona, they're 1.5 million degrees. So that region represents an incredibly dynamic area. There's a lot of physics going on in there. But so we'll see that. Now we are in solar maximum. So there's a lot of activity on the surface of the sun. So we expect to see a pretty dynamic view. We expect to see some streamers, usually when I'm talking to folks, I compare it to crazy bedhead, where you've got hair going off in all directions. So with this,
So what you're saying is right now, the sun is having a bad hair day, and in 2017 is kind of having a good
It was having a better hair day.
It was having better.
Yeah, exactly. So we'll see these streamers coming off the sides. Now, what I'm hoping to see, which would be very, very rare, would be to see what we call a coronal mass ejection coming off the side. This is an expulsion of gas, a huge expulsion of gas that essentially blows a bubble of gas out into space. If we're really, really lucky, we will be able to see that.
Why are seeing those important to science?
Well, seeing them in a coronagraph is of some level of importance, but really with coronal mass ejections, it's once they get to the Earth, that's when we start caring most, because that's what triggers auroras, that's what triggers space weather, and a number of other effects.
So we could see one of those, and then there would be auroras in like Antarctica or something.
Well, actually, if we can see it on the sun, if we can see it during totality, it means it's the direction of the coronal mass ejection is heading away from the Earth.
Oh, to the
so we
side,
don't
yeah.
have to worry.
Okay.
Well,
that's good.
yeah, that's a good thing.
Okay, so during totality, that's what we see when we look at the sun.
Right.
What about the rest of the sky?
The rest of the sky, you probably see some of the planets, some of the brighter planets. Very likely you'll see Venus and Jupiter, and maybe one or two others. It really depends on atmospheric conditions and a number of other things. If you're super lucky, you will actually be able to see a comet just up, I believe it's up and to the right of Jupiter.
And well, where's Jupiter going to be?
See, more or less directly left of the sun.
Left of the sun is Jupiter,
right?
And up and to the right, so sort of above the sun,
right,
would be maybe a comet.
Maybe a comet.
Maybe. A comet.
If you have binoculars with safety, you have to be careful with binoculars. You don't want to be too close to the end of totality and using binoculars.
Yeah.
So you just got to be careful.
Yeah, we just.
Yep. Yeah. But with binoculars during totality, you might be able to see that particular comet.
Very cool. Okay, so we know what we're going to be seeing in the sky. Will be stars or just planets?
It's going to be probably both stars and planets. You might see some other brighter stars.
Okay. Then on the ground, what will we'll say, yeah, on the ground, what will the experience be on the ground?
All right. You'll notice the temperature. First thing you'll notice is the temperature going down. You can probably expect on a day like today, probably 10 degrees or so. You may feel a breeze coming in because of pressure changes, because of the shadow of the eclipse over there, as it's heading towards you. That can create a ground breeze. You might see the solar snakes, you never know. But during totality itself, it's going to be like twilight. You're going to see the eclipse in the sky going on, those planets. So.
And can you actually see the shadow of the moon like approaching?
If you're on an airplane, yes, you definitely can. I've seen images taken from the Concorde a number of years ago, where you can actually watch the shadow move across the surface. If you're on the top of a mountain or something and you're looking in the right direction, yeah, you might be able to see the shadow coming towards you.
Cool. What about all our friends in cloudy regions? We actually flew into San Antonio and drove up here because it was supposed to be sunny down there, but it's not. It's a little cloudy. So, but can folks who are in cloudy regions, what will their experience be like? How can they still enjoy it?
Well, honestly, an eclipse is a full body experience. Yeah, we immediately think of the visuals because that's what we see posters on and things like that. But really, as the temperature comes down, you might feel sunlight on your skin changing a bit, but you definitely will hear differences. Animals think it's time to go to bed. So some animals will head for their homes. So those animals, you won't hear them anymore. Other animals will think it's time to wake up. In San Antonio, it's a little early for locusts, but if there were locusts in the area, you might hear them quiet, and then cricket sounds increase. So animals are really sensitive to eclipses. So listening for them will be very, very different.
And so if it's cloudy, it presumably still gets pretty dark.
Oh, it definitely still gets pretty dark. Yeah.
So it'll still be a pretty cool.
Oh, you'll know the eclipse is going on. Absolutely.
Great. Okay, so we've talked all this about safety. You got to wear your eclipse glasses until totality. How do you know when to put them back on before the sun peaks out?
That is a little bit trickier. But fortunately, you might actually see a little Bailey's beads to let you know. If all of a sudden you see a little flash, you might want to have them ready.
Yeah.
As totality is going on, don't stick them in your pocket. It's only here. It's 4 minutes and 11 seconds, but that depends on where you are. So don't stick them in your pocket. Have them in your hand, ready to go. And if you notice, gosh, totality's been going on for a while, might be time to start getting them close to your eyes, because as soon as that very first flash, you want to make sure you have them on.
That's great. And I think we have some time for some audience questions now. I want to make sure we have about 9 minutes. So let me see if we have any questions from our audience. Okay. Can you tell us a little bit more about the impact of the eclipse on pets and animals? Why are pets and animals so affected by this eclipse?
Well, they are very, very accustomed to paying attention to nature. Pets less so, because they hang out with us and we have a relatively artificial life. We turn lights on because we're not ready to go to bed. So pets tend to follow that a little bit more. Animals out in nature, they are very tuned in to what's going on around them. When the sun goes down at night, it's time to go to bed or it's time to wake up, depending on the animal. So when an eclipse starts, gosh, all of a sudden it got dark really, really fast. It must be time to go to bed for 4 minutes. And then they wake up again once the eclipse is done.
It's fantastic. Any other questions from the audience? Okay, so this pattern of eclipses, we had one 7 years ago.
Mhm.
Now we are having one, and then next was 20 years away.
That's right.
Why is it so weird?
That's an excellent question.
Wait for this train.
It can do.
The trains were not supposed to be running today, but apparently they didn't get the memo.
Okay.
So why is the pattern so irregular?
It feels that way, doesn't it? Well, as it turns out, eclipses happen all the time. They happen every 18 months or so. And it really has to do with just the alignment being right. But the vast majority of the time, those eclipses are taking place over the ocean, over the poles, over the desert, over places where there aren't people. So it is fairly rare for them to happen over populated areas, very populated areas. We're lucky this time. We've got 32 million people potentially doing this. And in fact, there's another one in Spain in 2026. If I'm not mistaken, there's actually one in 2025 in over a very small part of France. That's an old memory, so
Okay,
caution.
we'll fact check that.
Yeah, definitely.
Fact check that before you book your flights.
Yeah, please. So they happen frequently. It's just they have to happen over populated areas for anyone to pay attention to.
And this one's so special because it's over such populated big
Over
cities.
incredibly popular. It's like tracking right over major cities.
Yeah.
It's great.
Any more questions? So, sorry, one more time. That question is, why do we see so many half moon shadows during the eclipse? Tell me about these shadows.
Half moon shadows.
Yeah, I think that's actually like referring to the sort of the pinhole effect, where if you make a sort of pattern with your hand, it creates the equivalent of a pinhole, and you see that with shadows as well in nature.
So you're asking how a pinhole image forms?
Yeah, I think that must be what it is.
Okay.
Because and the crescent-shaped shadows from because in nature we normally form those shadows as well.
I'm just not sure what you mean by crescent-shaped shadows. So if you mean the crescent shape, the bright crescent shape of the eclipse, is that closer? Okay. So when you've got a pinhole image forming, whatever your object is, okay, light from the top of the object passes down through that hole and then down onto whatever the surface, there we go, passes through the hole and then down onto to the surface. Light rays from the bottom of the image pass through the hole and then form the top of the image. So any image that we see is going to be the mirror flip of the image that you see in the sky.
So it's not exactly a half moon image. It's actually an image of the eclipse.
It is an
being
actual
created
image of
either by a pinhole projection that you create, or sometimes in nature. I think that can just happen.
That's right.
That can happen.
And those pinhole images aren't all that special. They occur naturally. If you're lucky enough I grew up in Texas. I grew up on a farm. So we had a barn and there were nail holes in the wall. And occasionally you could actually see images of scenes from outside. You could see trees moving and so on through these projected images. So these are real images.
So those shadows are real images of the eclipse. Okay, so final question. Is it true? Okay, so is it true that the moon is drifting away and that we will one day not see eclipses on Earth? And when will we see our last one on Earth?
What a fantastic question. Yes, actually, it is true. The moon is very slowly moving away from the Earth. With every year that goes past, it moves away by about 2 centimeters, about 1 inch or so. In the next, and I hate to give a number, we would have to fact check this, but this is on the order of 50 million years. We will no longer be able to see eclipses of a sort. We will no longer see total solar eclipses. We will see annular solar eclipses. Those will go on until the Earth is gone.
I think I read somewhere maybe a few 100 million years. So definitely fact check exactly how many, but it's a while from now. We have a while.
We have time.
For at least your lifetime, you're going to be able to enjoy eclipses. Patrick, thank you so much for joining us. I also want to thank everybody who joined the live stream, everybody who submitted these amazing questions. I think everybody who submitted these amazing questions. I'd also like to thank the Gordon and Betty Moore Foundation, who helped fund this live stream. And hey, everyone, go out there, have a blast, be safe. It's the last time in 20 years in the States, so, you know, let's go do it.